Hi, I'm Laszlo Sado from Emory University, and I'm going to talk about research in my lab that we've done at the interface of machine learning and optimal transport. This has been joint work with Stan Osha's group at UCLA, and much of the work is due to my excellent student, Xingjian Li, and Derek Onken, and my former student, Semi Wufang, as well as two other postdoc in Stan's lab. And I also like to acknowledge our funding agencies. I'm going to talk about two examples in this talk. So one is optimal transport using machine learning. Here you're given an initial density rho 0 in the top and a target density rho 1 in the bottom. And the goal is to find a mapping F that is a coordinate change so that the densities are aligned at the end of the day, and there is a Jacobi determinant coming in from the volume change. This is a famous Monge-Ampere formulation. And it's a big challenge to overcome the curse of dimensionality that arises when D, the spatial dimension here, gets very large. The other direction, so using optimal transport to improve machine learning, is manifested in my second example. That is motivated by generative modeling. Here you are given samples from rho 0, so the setup is almost the same, but you're only given samples from rho 0, and rho 1 then will be a standard Gaussian. And you want to find, again, as the same transformation that maps between these two different distributions. However, the loss function has to be different as it cannot involve the rho 0. So here you can maximize the likelihood. And we won't show it, but both formulations that we can derive here are going to be quite equivalent. So here our goal is to come up with efficient numerical methods using optimal transport that improve the reliability and the efficiency of these models. And the work I'm going to present is basically consisting of these two papers also. Okay, so let's start with the relaxed optimal transport formulation. So here you have an optimal control formulation of the problem where we have a functional J that depends on the control V and the state rho, and the objective functional measures the transport cost. Here's the L2 norm of V times rho, plus the terminal cost that penalizes deviations of rho at time 1. So rho is now going to have a time dimension compared to rho 1, the target. The time evolution of rho is going to be governed by the continuity equation, where the velocity is basically the driving force when the initial condition is rho 0. The terminal cost, you can think about the KL divergence in my examples. So here's the density evolution that we computed after solving the problem. So you can see that basically all the mass is pulled to the center to match the target density. And then we can also define rho at time 1 as the push forward of rho 0. So that's the first formulation of OT that we're going to look at. Another view is to look at it from a microscopic perspective. So here we can define an agent at a position x in time t, and think about the problem from the perspective of this agent. They have to choose the density that minimizes, the velocity v that minimizes this functional here. So we have exactly the same transport cost and a terminal cost g that depends on the final position of the agent and the density around that point. And the motion of the agent is going to be governed by this ODE here, which defines a curve, which is the characteristic curve of the continuity equation. A few notes. So the G here is related to the one from the previous slide. The agents in the end interact through the density rho that is a part of G. And the transformation from the first slide you could define now as you map a point x to z x, 0 at 1. So when you start integrating the characteristics from 0 to 1. And now if you look at the picture again, basically we could have the initial agents being spaced here at time 0, and then they find their way to the center at time 1. It's going to be useful for the next slide actually to define the value function. So the value of an agent state xt is going to be the minimal value of this functional up here. So the minimal transport cost plus terminal cost. The value function we denote by phi, and optimal control theory actually gives us a lot of information about the properties of phi that are going to be useful in our approach. So here is the classical result called the Hamilton-Jacobi-Bellman equations, which are the first order optimality conditions for the relaxed OT problems that we have looked at. And here the first equation is a Burgers type equation that goes backward in time and has a terminal condition that depends on the terminal cost. And that is basically an equation for phi. And it's a result, it's actually quite a nice result, that the velocity is going to be the negative gradient of this value function. So if we plug this in, we have a system now of two PDEs that are coupled, the continuity equation and the HJB. They have a forward-backward structure. So this one has terminal conditions, this one has an initial time condition. But solving this system is going to be a solution or give us a solution to the OT problem. So I've depicted here the value function for our problem. So yellow is bright, is large values, and blue are small values. So you can see that the negative gradient would point into the center, which is expected. And you can also see that this evolves basically and actually drives the evolution of the density here. Okay, so now basically we need to put things together. So we've seen three options for solving the problem. Variational formulation on the first slide. We can choose to replace the velocity by the negative gradient of the value function to reparameterize it. We can alternatively use a microscopic view. We can solve basically the JXT for different axes that are then interacting, or we can compute the value function by solving the system of high-dimensional PDEs. Each of them has pros and cons, and what I'm going to show you is how to combine the advantages, but forget about the disadvantages in order to tackle the curse of dimensionality. So specifically, what we'll do is we'll use a variational approach. We will plug in v equal to minus grad phi. We will eliminate the continuity equation with a Lagrangian PDE solver. This will give us a mesh tree and parallel method. We'll parameterize the value function with a neural network, which are universal approximators, don't require a mesh. And I'll show you a little bit about how to make that actually relatively efficient computationally. And then we'll also use the property. So phi will be the variable we're optimizing over, and we will impose violations of the HJB as a penalty, because that has, in numerical experience, really boosted our convergence that we observe, and also allow us actually to solve the problem more efficiently. Okay, so I want to show you next how to solve the continuity equation with the Lagrangian method. Again, here it is with the negative gradient of the value function governing the flow. And it's true that along the characteristic, you can actually immediately write down the solution to the continuity equation. So rho at z, comma t, which is a point on along the characteristic, is related to the initial density rho 0 and the volume change induced by the transformation. So if I play this here, these are the characteristic curves for a bunch of agents or points x in the beginning, and you see, so they are pulled toward the center in our example. And then in the end, their mass actually accumulates, and this accumulation is kind of given by the determinant of the Jacobian here. Okay, so now you may wonder, how do you compute the determinant of the Jacobian in high-dimensional spaces? There's actually some good news. So first of all, we will only need the log determinant if we use a KL loss. And there is a Jacobi identity here that we can use to basically, along the characteristic curve, integrate the Laplacian of the potential of the value function phi. And so now we replace basically the determinant computation by an integral in time. And this integral can then be lumped together into the ODE that you solve for z, and can be parallelized trivially over different points. So all this we will put into our learning problem, which looks a bit intimidating, but we'll walk you through there. So we have an expected value that replaces the integral in the variational formulation. We have the CL here, which keeps track of the transport costs by accumulating the norm of the gradient. We have G, which is the terminal cost. We have then the two penalizers here, so CH and this part here penalize the HJB violation. So this at the terminal state, and this is in the intermediate time points. We discretize, so this is an optimal control problem. now, we discretize the ODE using NT steps in an arcade-4 scheme in our case. We keep this fixed in a discretized optimized fashion. We use Monte Carlo integration for the expected value, importance sampling if available. And then we can solve this with stochastic approximation or stochastic average approximation schemes. There is no grid needed, and the computation can be actually parallelized trivially, as typical in neural networks. The big question to answer on the next slide is which parameterization we use for phi. Because especially here, you can see you need the gradient and the Laplacian in order to compute the ODE, which is not always readily available in neural networks. So what we specifically do is our network takes x and t as an input, so it's a state, and then it consists of the first term that has a neural network n in here, and it can be pretty much any neural network, and then a quadratic part here, which allows us to easily represent affine shifts to the system. And in our case, the n here will be a ResNet, and which has the classical forward propagation that you are used to. The first layer here actually allows us to expand or decrease the hidden dimension to small m, and then the rest of the layers will just keep that particular width of the network. In the end, you multiply the output vector with w, which is also a weight. A few notes. So remember, we also need the gradient and the Laplacian of the network. The temptation would be to just use automatic differentiation, which is readily available these days. However, that's typically limited to matrix vector products of this form. So you would basically compute the Laplacian as a trace of the Hessian, and you would need d passes of automatic differentiation to compute Hessian matrix vector products. That is clearly expensive, so it's been suggested to use trace estimators. However, they will add inaccuracy to the volume estimates, which we would try to avoid. So what we found better is to derive the derivatives manually, and we actually came up with an efficient way to implement this that scales linearly in the space dimension, quadratically in the width of the network. And the implementation that we have is actually super fast. Typically, it runs at the same speed as computing only one term here. And that is because most of these computations have dense matrix operations, and that clearly parallelizes very well on GPUs. A quick comparison to a method that is based on a Eulerian approach, so with a fixed grid. Clearly, this is only going to happen in small dimensions, so we'll stick with 2 for now. This one has a conservative finite volume discretization. We can use a Newton's method to solve the resulting convex problem. So we really have the optimal solver on that particular discretization. And what we found to our surprise is actually that the machine learning method really compares very well. So you almost see no differences here in this column, which is the machine learning method and the benchmark method. And you see also basically the same loss values here, or even slightly better losses for the machine learning approach when a different discretization is used to identify or to compute the loss. It's a completely different ballgame. So the Eulerian method has a convex problem with 3 million unknowns. The machine learning framework has only 600 parameters, but of course the learning problem is non-convex, which makes this actually a really tough benchmark and a very nice result. More nicely actually is also that the value functions that we compute really completely agree almost, at least where we have agents, which makes this method really a competitive option even in 2 dimensions, also because of its simplicity in the implementation compared to the Eulerian approach, which needed sparse matrices and saddle point solvers and all that kind of stuff. These results also scale to higher dimensions, but I'm going to use a machine learning application now to show you that capability. So the generative model we are going to look at is continuously normalizing flows, and specifically here, I'm going to regularize it using optimal transport. And we call our approach that results OT flow. Here, again, we are only given samples from row 0, and we want to find the value function so that the flow maximizes the likelihood. And this reads as follows. So row 1 is going to be a standard normal distribution. So we can basically use the first 2 terms to compute its negative log likelihood for each sample. And then we have the transport cost and the HJB violation as before. So here's a sketch. So you have your samples here and you have your row 1 here, the nice bell curve. And then what happens, I want to highlight the importance of the optimal transport part. If you don't have it, you may end up with characteristic curves like this. And that would be an optimal solution, since the problem actually only depends on the terminal state and you reach the correct points here. However, it's not nice numerically because you have very complicated characteristics. So this will take you a lot of computational power to compute very well. And second of all, I think the problem not having a unique solution also may be to be avoided if we can. So adding these two terms does that. So it does two things. It gives you a unique solution, but also it makes sure that the characteristics are a straight line. So you can prove that with OT theory, and a straight line is much easier to integrate in an ODE solver than a twisted or curved line with other works. And we are by far not the only ones who have seen the benefits of OT in this area. So here are 3 more references for that. You can use this mapping then to generate samples. So you can sample the red dots and create more blue dots, or you can estimate the density of the blue dots as well. Here's just showing the flexibility in 2-dimensional data sets. So the top row shows some samples of complex distributions. And below, I show some density estimates obtained with our model. The real game is in higher dimensions, though. So here are a few examples with a bit higher dimensions, I think up to 100 or so. And what we see here left is the accuracy measured in max mean discrepancy. Ours is a triangle. You want to be close to the left, which means left and bottom. So this means low error and small networks. And we kind of move the state of the art more or less consistently, except for this one data set to the area we want to be at. And this one shows the efficiency. So this is a training time in hours, and this is testing time in seconds. And you want to be really close to the origin here, and the arrow is really pointing the right way here for our method. You can have 2 to 22 times fewer weights, and you have considerably much faster training and testing times compared to all the existing approaches that we've tested here. Okay, so let me briefly sum up. So the first application, or the first paper here on the left, uses machine learning to solve optimal transport problems and scales to high dimensions, which is our main motivation. It combines the Lagrangian PDE solver, it combines HJB panelizers, and to our surprise, it was competitive to convex programming even in 2 dimensions. In the second part, I applied this method back to a machine learning problem, which is continuous normalizing flows. And the optimal transport really gave us a lot of well-posedness and efficient time integration here. We, together with the discretized optimized approach, HGP penalties, we actually have a really nice speed ups consistently. There are more results in the paper, and there is more to learn from my collaborators, Levon Nobakian, who gave a nice talk on mean field games, which is actually the extension of this work. Is a much more general setting where these methods, where we have applied these methods. And my student, Derek Onken, gave a really nice talk at the AAAI meeting, which is only about 17 minutes. Both are hyperlinked here. You can get the slides from my website. And we have a Python code or PyTorch code as well. And I'm happy to discuss more with you. Thanks a lot.